we will continue the talk. So the next presentation is by Dr. Robert Barlow. The title is Canonical NH3H2N2 Air Turbulent Flames, State of the Art and Future Challenges. Dr. Barlow, could you start?
Yeah, let me see if I can share my screen.
Okay, please.
And see if it starts. So can everybody see my screen?
Not yet.
Not yet. Oh yeah, I forgot to click a button. One moment. Let's see if that works.
Yes, I can see your screen.
Good, good. Okay.
Okay, please start.
Yeah, thank you. And thanks to the organizers for inviting me. I'm a relatively newcomer to the topic of ammonia combustion, just within the last couple of years with some consulting work. But I think what the purpose of this talk really is to take some of the experience that we've gained over quite a few years in the turbulent, fundamental turbulent combustion community, research community, looking at canonical flames for primarily methane and also some other simple fields, and using detailed experiments on those canonical flames to really make progress in two areas. One is to gain a better fundamental understanding of the interactions of turbulence, chemistry, and molecular transport. And the other is to provide a series of progressively more difficult or progressively covering different topics, computational test cases that can be used to challenge the development of predictive models for various aspects of turbulent combustion and the interactions of turbulence, chemistry, and transport. So I want to also thank very much the several groups that have contributed some recent research results to this talk, and I'm going to be using some examples from some of that research, some of which is not yet published, so I won't be going into very much detail at all on the unpublished work. I'll just be showing it as a indication of how far we've progressed just in the recent past on fundamental measurements in turbulent flames of, in particular, blends of ammonia, hydrogen, and nitrogen that represent partially cracked ammonia. So I want to start essentially setting the stage by briefly covering some very interesting results from a nice experiment from Norwegian University of Science and Technology. And this is work by Sam Weissman. The experiments involve looking at lean blow-off limits of ammonia, hydrogen, nitrogen blends, or a particular blend versus methane. And the selection of the blend shown, let me just get my laser pointer going. Selection of the blend here was picked to match the laminar flame speed and the laminar flame thickness of methane across the range of lean equivalence ratio. And that's according to the San Diego so-called short mechanism that was used for the ammonia calculations. And so an interesting aspect of ammonia that is going to present some challenges for combustion modeling, I think, is that even though the laminar flame speed and the flame thickness are very similar for this mixture to methane, the extinction characteristics are very different. And the graph that I just showed has extinction times for PSR calculation and then also twin flame, opposed twin flame simulations. And if we consider this just for an example, equivalence ratio 0.6, the ammonia blend is a factor of nearly 4 times more robust. The extinction strain rate is a factor of 4 higher, translating to a shorter time scale compared to methane at the same equivalence ratio. And that has some significant implications for stability of flames and the practical operation of combustors. And so I'm just going to quickly show this blowout event, and then we're going to go to the next slide and talk a bit more about this. So here we're looking at comparisons of turbulent blowout behavior. And so the graph shows the blowout velocity versus equivalence ratio for the ammonia blend, ammonia hydrogen blend, and for methane. And the OH cliff images on the left show a series of images stepping backwards in time from the blow-off event by 1 millisecond, 10 milliseconds, and 1 second. And we're focusing on two pairs of flames here. For the first pair, we consider operation at the same equivalence ratio, and the ammonia blend has nearly a factor of 12 higher blow-off velocity, much more significant for the turbulent flame than we saw for the laminar difference in laminar flames. And if we just consider constant velocity, the ammonia hydrogen blend stays stable to a much leaner equivalence ratio. And so this is an indication of at least one aspect of ammonia combustion that we want to be able to understand in much more detail. And we want to be able to use some detailed diagnostics to understand on a fundamental level why this is happening and whether we can accurately predict it. So that brings us to a sort of general question. How should we approach turbulent combustion fundamentals for these ammonia hydrogen blends? And to begin that discussion, we want to list off some of the aspects of turbulent ammonia hydrogen combustion that we expect to be important challenges. And that is in the context of predictive modeling, but also in the context of really understanding the fundamental interactions of chemistry, molecular transport, and turbulence. First on the list is what I just showed in the previous slides, this high resistance to extinction and blow-off. And that very likely is at least partly due to the effects of differential diffusion of H2 in the ammonia hydrogen blend. So differential diffusion of hydrogen is certainly an important topic to understand and be able to measure in turbulent flames. And as a previous speaker emphasized, NOx emissions are very important to be able to predict for ammonia. And there are some relatively significant challenges to doing that in terms of this rich, lean kind of combustion, at least in power generation terms. So the diagram on the right of the slide is a bit of a cartoon that is a kind of a guideline that if we want to understand very fundamental turbulent combustion processes and apply the sort of diagnostics that we need to gain insights on those fundamental processes, we should start by eliminating or designing burners that don't include any more complications than necessary. So we're going to try to avoid some of the complications or features of turbulent flames that are on the right side in non-bold font, and try to focus in on combinations of the already complicated enough inputs that are in boldface. And we also want to learn from past experiments and DNS on canonical flames of methane and hydrogen blends, including, say, just methane hydrogen, as well as syngas. And an important point is that if we want to understand the interactions of turbulent flow, molecular transport, and chemical kinetics, and also to be able to test turbulent combustion models, we're going to need detailed data sets. And in the past, we've applied diagnostics to get multiple scalars, major species and minor species simultaneously in some cases, velocity. And we want to be able to compare point statistics with the models, as well as understand aspects of the spatial structure. And in some cases, it's very valuable to to be able to use high-speed diagnostics to look at flame dynamics. So what sort of canonical test cases should we be looking at for ammonia hydrogen flames? That's really going to be a topic of discussion, and what I'm going to do is present some possibilities and some examples. But the first important topic is that we need to develop quantitative multiscalar diagnostics for ammonia flames. And there's really been a huge amount of progress made over the last year, especially at KAUST in this direction. I'll be showing some results on those experiments and those developments. We should consider previously used burners. There are several burners that have been used in the community over a number of years that have interesting properties that are well understood in terms of computational applications. And we already know quite a bit about the way methane flames behave with these burners. So some of these burners may be very good targets for investigating ammonia hydrogen blends as well. An important point that is really a major theme of the TNF Workshop series is that it is highly valuable to collaborate with modelers when you're designing experiments. That doesn't always happen, but it really has some great benefits when it does happen, or can have some great benefits. And that involves making sure that the geometry is something that's computationally accessible, that the flow conditions are appropriate, that you don't have zones of separation, flow separation, things like that, that are very difficult to predict. And also understand what the data needs are of the modeling people to test the models that they're trying to develop and validate. So we need well-defined boundary conditions. It's best to cover experiments that, or to run experiments, design experiments that have parametric cases that run across critical transition points in the behavior of the flame, such as blow-off. And to apply complementary diagnostics, which means it's often very nice to have the same burners visit different labs, or have multiple copies of the same burners that can be used in different places to apply complementary diagnostics. So let's look at some of these examples from the TNF Workshop. And this workshop series is very familiar to some of you and maybe not so familiar to others, but I'll just briefly go over some of the things we've looked at. And over the years, we've looked at a variety of different flames covering premixed, stratified, partially premixed, and non-premixed flames. And also pushing across different regimes within those different combustion modes. And one can certainly say that the interactions of turbulence, molecular transport, and chemistry are expressed differently in these different combustion modes and regimes. So starting with differential diffusion, there are several examples of flames that have been very useful in understanding the effects of differential diffusion in turbulent flames, where it's important, where it's not. And that includes both non-premixed jet flames and premixed and stratified flames. We've done a lot of work in the context of turbulence chemistry interaction to look at local and global extinction, blowout. Again, in both non-premixed and premixed flames. In early years, we combined NO diagnostics with the Raman scattering and looked at NO formation in primarily jet flames. And most recently, there's been a fair amount of work looking at local reaction zone structure in what we call multi-regime flames, where a local flame zone or local flame structure can include both premixed and non-premixed characteristics, or premixed non-premixed reaction zones that are in close proximity and can both be contributing significantly to the heat release. So I'm going to give two examples from past work on the effects of differential diffusion in methane jet flames, and then premixed bluff body flames as a second example. And the flame that we see here is well known to some, the Sandia Sydney piloted jet flame. And what's shown on the right are plots of the species, major species mass fractions versus mixture fraction. And the same in the two graphs. The lower graph shows a relatively low Reynolds number flame. I would call this transitional rather than turbulent, with measurements taken just 15 diameters downstream of the jet exit, relatively far upstream in the flame. And the second case is at a higher Reynolds number and taken farther downstream. And the solid and dashed lines in these plots are the unity Lewis number laminar flame calculations corresponding to the fuel air mixtures on either side, the fuel jet and the air, and multi-component transport as the dashed lines. And what we see is that particularly for hydrogen, the behavior of the flame is very much like the multi-component transport laminar flame. The behavior of the turbulent flame aligns very well with the multi-component transport. In other words, differential diffusion is very important in the near field of a jet flame at low Reynolds number. And then farther downstream at a higher Reynolds number, the measurements align very well with the unity Lewis number calculations. So that's a general insight that's come from that sort of experiment. And a premixed example is shown here with the so-called Cambridge swirl burner. This particular case is non-swirling, and it's also fully premixed. It's not stratified, running at 0.75 equivalence ratio. And there's an interesting transport effect that I won't go into explaining in detail here, but as you go through the reaction zone in the near field above the bluff body, where the flame is stabilized, from the reactants into the products in the recirculation zone, the measurements go from the expected reactant conditions to something that's not expected. The carbon-hydrogen ratio is much higher than it should be for methane air. The equivalence ratio in the products is higher than it is in reactants, and there's excess CO2 over what you would expect for just the methane, simple methane air combustion. And this is all due to a combination of differential diffusion and the fact that the reaction zone is in a shear layer where the essentially hydrogen species are transported downstream and never make it back into the recirculation zone. So it's a very important effect, unexpected effect of differential diffusion that requires measurements of the major species, in this case based on Raman scattering, to be able to explore or even discover that effect happens. So a priority for canonical experiments on turbulent ammonia flames is to develop Raman scattering for ammonia. And Gaetano Menotti at KAUST and his co-workers have made a huge amount of progress in just the last couple of years in this direction. And they are using laminar flames, measurements in laminar flames compared to calculations. This is running at 5 atmospheres pressure, and high pressure is a main theme at KAUST. And they've also developed they're developing and validated a technique or the Raman scattering for ammonia, but also discovered a method of measuring NH2 using the same diagnostics. There's also a work going on in Darmstadt with two universities there with Andreas Reitzler and Dirk Geyer and their co-workers. And they also have developed a laminar post-head burner to use to develop Raman scattering as proposed work for ammonia, essentially using a method that's going to be quite similar to what Gaetano has done. And they're going to be combining that in open flames with Rayleigh scattering. And also proposed for future work is to include NO fluorescence measurements in that facility. So I'm going to use a couple of, I'm going to go give a little bit of information. This may not be exciting for everyone, but it's exciting for a few of us on what the Raman diagnostic actually looks like for ammonia flames. And this is a slide from Robin Schulthus at Darmstadt, showing a premixed rich Bunsen flame. The Raman 1D Raman measurements showing nitrogen and water in the products, and hydrogen, oxygen, ammonia, and hydrogen, oxygen, ammonia in the reactants. And the corresponding Raman spectra are shown here, with being the ammonia spectrum. And this is what needs to be calibrated for quantitative measurements of ammonia. It can't be calculated from theory, or that's not available to us. And then within the reaction zone, there's a broadband interference that is going to have to also be measured and corrected for. The good news is that compared to methane, the challenge of doing ammonia Raman scattering is relatively simpler, and so there's good prospects for getting very good quantitative measurements of all major species in these flames. And Gaetano has done some really nice work with students at KAUST. They're using this opposed jet burner and measuring the Raman scattering signal from ammonia in an opposed laminar flame, where they can do the calculations and use those laminar flame measurements to determine the temperature-dependent response of ammonia, the ammonia Raman scattering. And that can be done with some confidence because there's essentially no significant difference in the predictions of various different mechanisms in terms of the major species concentrations versus temperature in these flames. And there's only a very minor effect of strain rate, so that there's those calculations can be used essentially as calibrations. And the result that they get is a relatively low temperature dependence, which is good because that doesn't cause an increase in the species uncertainty if there's uncertainty in the temperature. But as I said, there's a bonus that the interference can be correlated or can allow a measurement of NH2 with no extra cost using the same equipment. And this illustrates again the relatively high interference you get in between the nitrogen and the ammonia Raman spectra. And it turns out that in the measurements, the behavior of this interference with temperature, or the magnitude of the signal from the interference, mimics the behavior of the concentration of NH2. And so if you pick a mechanism, in this case, pick one that's in the middle of the pack, you can use that to calibrate essentially the NH2 signal and translate it to a concentration. And that does depend on the mechanism, but the difference between the different mechanisms shown here is not too great. It's roughly plus minus 20% at the peak, and that's valuable. It would be even more valuable if there could be a direct measurement using tunable dye laser absorption, for example, of the NH2 concentration in a reference flame that could then be used to pin down or do a real calibration on this signal that we're measuring with the Raman system. Another area that's very important to consider is, in terms of laminar flames, is the extinction strain rate for opposed jet premixed laminar flames. And this is in the context of that turbulent bluff body flame that we saw, where we have a very high extinction or high blow-off velocity for the ammonia. So the NH2 predictions from various different mechanisms were not very different, but when we go to the extinction strain rate for ammonia hydrogen blend, in this case it's 30% hydrogen. there's a fairly large difference. And if we look at a 21% hydrogen difference, it's even more significant and over a factor of 2 over most of the range of equivalence ratios shown here. And that gives a motivation that if we want to really understand this extinction process and be able to predict that, we need to do some laminar measurements of laminar extinction of premixed flames of these ammonia hydrogen blends as a priority. And that is some work that's proposed by Darmstadt. I'm not very familiar with the literature. My understanding from what I've read is that there's only pretty limited data on non-premixed extinction experiments. So it may be that the similar experiments on post-flow laminar non-premixed flames would be very valuable for these mixtures. So this is the last slide on diagnostics, and we'll go on to some discussion of turbulent canonical flames. And this is a very interesting contribution from Bo Zhao in China and his students. They've demonstrated a technique not yet published, so thanks for sharing this pre-published work. It's a combination of diagnostics where they've picked a wavelength, a single wavelength that allows measurements of fluorescence of both ammonia, NH3, and NH. And what's shown here is a couple of samples or samples images from 2 different flames. The image on the bottom is a higher Reynolds number, so it's more wrinkled. And the images that you see are the radio scattering, ammonia fluorescence, and NH laser-induced fluorescence. And this is similar to what one would get from, say, CH fluorescence and maybe formaldehyde in a methane flame, in that especially from the combination of the ammonia and the NH, you can see where the reaction zone is, and you know which side of the reaction zone you're on. And so there's potential to identify or use this technique to look at the structure of reaction zones, identify where there's local extinction, get some quantitative information on the flame thickness and curvature. There's perhaps potential to use high-speed diagnostics with this sort of approach to look at dynamics of, say, the blowout process, and to be able to see where you have unburned pockets of fuel and where the reaction zones are still healthy and where there's local extinction. So this is a very, I think, interesting prospect for diagnostics in turbulent flames for the future. Now let's regroup a little bit back to the topic of canonical flames, because I wanted to share some of the progress on diagnostics and emphasize that detailed measurements of major species and minor species are going to be really important for understanding turbulent ammonia combustion on a fundamental level, and for providing data sets that will really test the predictive capability of combustion models. So back to the list of key phenomena that we want to investigate. There's stabilization, local extinction, blowout, differential fusion, NOx formation and emission, and pressure effects. Measurement needs and diagnostic challenges. As I said, there's already great progress. We've already seen a lot of progress in extending our own methods to ammonia hydrogen flames. I'm not sure I would have been able to give the same summary a few months ago because the work was still ongoing and I hadn't seen it yet. But thanks for Gaetano for sharing that. That's relatively recently published stuff. We want to combine those Raman diagnostics with quantitative measurements of NO, OH, NH, and NH2, not necessarily all at the same time, and making some of those quantitative will be a challenge. We need to do baseline experiments and simulations in laminar flames, as I've already mentioned and given some examples. And then these 2D diagnostics, and particularly high-speed diagnostics, combining PLIF imaging and PIV, can be very useful in looking at reaction zone structure and things like blowout dynamics. In terms of selection of turbulent test cases, as I said, it's very useful to collaborate with computational people when you're designing experiments so that you are sure that the hardware is actually something that's computationally accessible in terms of gridding, in terms of the having an inflow condition that's not too complex in terms of the flow conditioning and how the flow is actually handled internally. It's very important to design studies that are parametric studies that cross critical ranges of those parameters in order to isolate as well as possible specific combustion phenomena. And we want to be able to design experiments or select burners that cover different combustion modes, premixed, partially premixed, and non-premixed. Most practical systems end up being partially premixed because many flames are lifted or are not fully mixed when they enter the flame zone. And it's important to collaborate both on the experimental design, but then also to use common burners and then collaborate on the comparisons with these experimental results with simulations. And that's, as I said earlier, that's been a major theme of the TNF workshop, and I think also is very important to apply as we move into this area of fundamental understanding of ammonia combustion. So some potential canonical flames to look at. First off, simple jet flames. We've looked at several types of jet flames or several different fuels within the TNF workshop listed here, and used those to explore differential fusion, NO formation, local extinction, mixing characteristics in turbulent combustion, and scalar dissipation. Recent work at KAUST has focused on simple jet flames, these being at elevated pressure of 5 atmosphere. And there's recently published work from Gaetano's group on 2 examples of partially cracked ammonia, 14% cracked and 28% cracked, corresponding to 18.4 and 32.8% hydrogen. They've applied Raman scattering, 1D Raman scattering, as well as 1D NO fluorescence. One of those papers is, or both, some of those papers are submitted to the Combustion Symposium. I guess both now are submitted to the symposium. And in terms of the NO diagnostic development, they've again used laminar flames to help with the calibration and the quantification of the diagnostic. And it seems to compare relatively well with this particular mechanism from Otomo. And I'll just very briefly show you, since it's not published and you won't have time to digest any of it, some work on differential diffusion from this paper and some profiles, mean and RMS NO in these turbulent flames. And so be sure to see these papers assuming they get accepted at the Combustion Symposium. Another category of canonical turbulent flames would be premixed buff body flames. We already saw an example from NTNU shown on the top here, and also the Cambridge example. And this is an example of a simple enclosed dump combustor. We also saw examples of those on the introductory slide for the workshop and from the previous speaker, from Professor Kobayashi. So a couple of comments on burners and design of burners. If we wanted to use them for these sort of detailed measurements, that they have to have optical access for Raman scattering. Again, they should be computationally appropriate. To bluff body burners, it's very important to, or can be very important to measure the surface temperatures certainly in the enclosed geometry, surface temperature can have a very big effect on flame stability. Because of heat loss to the walls, that needs to be accounted for in the calculation. And you want to push Reynolds numbers as high as possible. Measurement opportunities include measurements of the blowout process. We're using detailed diagnostics, such as Raman near blowout, but also high-speed diagnostics would be very valuable there. And try to understand what the influence of differential diffusion is on this very high stability or resistance to blowout that we see in the ammonia hydrogen flames. NO formation in combination with the temperature in major species, we need to know a lot of detail to really understand NO formation, and the list goes on from there. Another, I think, very interesting flame or configuration to consider is the jet in hot co-flow. This geometry was first proposed by Bob Dibble many years ago. And the purpose of it was really to be able to look at flame stabilization in a lifted flame stabilization in a high temperature without having the complication of a recirculation zone. So that's a sort of stabilization that happens often in, say, gas turbine applications. It also occurs in diesel combustion. And this simplifies the flow geometry, which was particularly valuable at the time because LES was not something that was on the list of realistic computational possibilities at the time. And so this simple flow geometry was very valuable. And it's proven to be valuable over time in several applications, including both non-premix flames, extending to mild combustion with the work from Boston Valley and also at Delft. And there have been premixed flame examples that some of which are quite well known, including the flame from Matt Dunn, piloted premixed burner from Sydney, and also Boja's flame that was he worked on at Lund University. And both of these flames were looking at very high turbulence levels, high Karlovitz number premixed flames. With non-premixed flames, you can investigate the flame stabilization without, as I said, without the recirculation. And the transition of stabilization from a flame propagation mode to an auto-ignition mode is something that can be very interesting and potentially difficult to predict accurately. An interesting challenge for models, which may also be very relevant for the ammonia hydrogen case. And there are unfortunately, several operational challenges to running a burner with a large pilot. And Matt Dunn, that's one of the experts on how one should design this sort of burner. One of the challenges in particular is that the large pilot eats a lot of fuel, and so and it produces a lot of thermal load in a lab. So it's something that has to be approached with eyes open. Another interesting flame that's been a workhorse over many years is the Sydney piloted burner. There are actually two versions of this. The homogeneous burner that was, for example, the original Sandia Flame D that's been used by many people for simulations. And a more recent inhomogeneous version where there's a central fuel tube that can be recessed away from or upstream of the nozzle exit. So that you have variable mixing of the fluid, partially premixed air and fuel as you leave the exit and go into the region of the pilot. With methane air flames, where methane is going through the central fuel tube and air is in that surrounding annulus, the blow-off velocity has this sort of characteristic behavior. As you recess that fuel tube further and further upstream, it goes through a local maximum or a overall maximum at a particular recess distance. In this case, is about 75 millimeters, and then drops back down to asymptote at what you have in terms of the blow-off velocity for a fully mixed, the normal burner. And Assad has been working, or with his group, working on some measurements with ammonia hydrogen and also hydrogen by itself, with a few examples, photographs shown here. But the behavior in terms of blow-off is actually quite different. And in all of these cases, with various blends of hydrogen and ammonia, the maximum blow-off velocity happens for the fully mixed case, the fully retracted fuel tube. And this is something that I don't personally understand, and I think Assad and company are still puzzling on this. But it's clearly different behavior from methane, and it's something that I think would be very useful for us to try to understand with some detailed measurements. So just to wrap up, probably gone over time. Sorry about that, by quite a bit, I see. And in terms of diagnostics, there's a huge amount of progress that we've made, but I think a few more steps in a direction of improving the detection for the Raman system in order to get better precision and signal shot measurements in turbulent flames is something that needs, or there's room for some additional work there. We want to be able to calibrate and quantify the NH2 measurements as well as the NH LIF measurements, probably based on some laminar flame diagnostics of absorption, and perhaps to get a better handle on uncertainties of the NF measurements in turbulent flames. They look quite good, but I think there's some room for better understanding of how accurate those measurements are. And I think we want to be able to put our heads together and try to identify the best combinations of simultaneous diagnostics to answer specific questions about ammonia combustion and emissions in particular, to plan for future experiments that would apply those best diagnostics. We want to be able to, probably in the not too distant future, start looking at comparisons of simulations with the simple jet flames. And then move toward detailed experiments on flame extinction, stabilization, and blow-off, including both the pre-mixed buff body flames and perhaps the Sydney piloted flames. And overall, the message that I'd like to emphasize is collaboration between the experimenters or among experimenters and modelers on burner selection design, as well as data needs, is something really to emphasize. And with that, I'll thank you.